Welcome back to the PLC Professor's Workshop. We are going to do another lecture in the RSLogix 5000 Studio 5000 course. We've already done a half a dozen, and now we've done some bits, we've done some rungs. Now we're going to actually start with some programming techniques. The first one we're going to cover is latch and unlatch. And the symbols, there's two symbols, one with an L and one with a U. And that's because the original device was called a latching relay. And a latching relay had two coils. One coil, if you energized it, pulled contacts closed, and then there was a mechanical apparatus that held it closed. And so you used a pulse of energy to close the contact, but it mechanically was held closed. So the latching coil was temporarily energized, and then it held in that position. And then the unlatched coil was another coil that pulled back the mechanical mechanism and let the contacts go back to the normal state. And that's why there's two symbols, one for latch, one for unlatch. Whereas the output energize instruction, OTE, has a two executions. If the rung's true, it turns on a bit in memory. If the rung's false, it turns off the bit. It has a true and a false execution. The latch and the unlatch instructions each have a true only execution. So if you have an L instruction, a latch instruction, the rung goes true, it tells that bit it's on. But when the rung goes false, it's silent. It doesn't do anything. The unlatch instruction, if the rung's true, tells that bit it's off. If the rung's false, it doesn't do anything. Just like the two coils on the original latching relay. And remember that in relay logic, you didn't have a scan. I mean, in real relays, electromagnetic coils with contacts, there was no scan time. You energized the coil and something happened, and you kept it energized to keep it that way. With ladder logic diagrams in a PLC, you have a scan. If that scan scans the logic 1,000 times a second, then 1,000 times a second, an OTE either tells that bit it's on or that it's off. A latch instruction, 1,000 times a second, if it's true, tells that bit that it's on, even though it's already on. It doesn't know it's already on. So every time the rung is true, it says you're on, you're on, you're on. If it's an unlatch instruction, and if the rung's true, then 1,000 times a second, it says you're off, you're off, you're off. If the rung's false, it just doesn't say anything. So keep in mind that you have a program scan, and that's what separates a real relay circuit behavior from relay ladder logic diagrams. Okay, let's jump in and play with the latch and the unlatch. Logic that remembers latch and unlatch instructions, and then eventually seal in logic. Both of those are methods of producing or creating logic that remembers past events. In your manual, we had you open up a former project, two rungs with in out, and it should have looked like this. If it didn't, not to worry. Just edit the logic on your screen, or if it's something else, save it and then rename it and then edit it to look like this. Or if you want more exercise with RSLogix 5000, create a new project, add your I/O modules, create any tags that go along with those I/O modules if you're not using the IQ6 XOW4, and then continue from here. So looking at this code, these two rungs of logic, if someone were to ask you to put these into words, in other words, to speak what these rungs say, you might say, rung 0 says that if local 1i data 0, that bit is off in memory, then turn on local 1o data.0, that bit in memory. Whereas rung 1 says that if local 1i data 0, that bit is on in memory, then turn on local 10 data 0, that bit in memory. Although this is true, those are both true statements, it is not a complete statement of the logic. Remember that when a computer program executes, it does exactly what you instruct, nothing more, nothing less. It does not read your mind. You may or may not be making an assumption like most of us, but I would assume that if the rungs are not true, then the bits would be turned off. Without knowing ladder logic, you might assume that. I think many people would have, because electrically, if you don't have a complete path, then the coil de-energizes. And this logic does behave that way, but that's not what we stated in the logic. So let's restate those two rungs. The complete logical statement for rung 0 says that if local 1i data 0, that bit is off in memory, then turn on local 10 data 0, that bit in memory, else turn it off, that bit in memory. And rung 1 says that if local 1i data 0, that bit is on in memory instead of off, on in memory, then turn on local 10 data 0, that bit in memory, else turn it off, that bit in memory. If you want to set a bit in memory to 1, that is, turn it on, you have to instruct it as so. Consequently, if you want to set a bit in memory to 0 or turn it off, you have to instruct it so. The emphasis that we are presenting here is that the OTE, output energize instruction, has a rung true execution and a rung false execution. If the rung is true, it sets the bit that it is addressing to 1, or to say turn it on. And therefore, if the rung is false, the instruction sets the bit that it is addressing in memory to 0 or turns it off. Not all output type instructions have both a true and a false execution. With your project in the offline mode, we'll change ours to offline. Open and place your cursor after the 0 on this memory location. Change it to 1. We're moving away from the logic that chattered, the scan-dependent logic that we did in a former lab where we had two OTEs addressing the same memory location. Now they are addressing two separate memory locations. That was the easiest method of editing the memory location that this instruction is addressing, but not the only way. You could have opened the addressing field, dropped down the list, drilled down to bit 1 of that same tag, and then selected it. Remember that the memory location is just text. You can drag and drop memory locations. You could have dragged this one over, assuming we don't have that one that has an O in it. You could have dragged this one over, change the I to an O. It could be lowercase too, see? And right away it recognizes that as a legitimate tag. That's why you see the reverse video on the rest of it. Then we'll put in a 1 and we end up with the same thing. This is kind of like working with a word processor. To further demonstrate this, double click on rung number 1. You see right here, that's just text. That is how this rung is stored. When you save your project, rung 1 is stored like that, right there. XIC, that's that instruction. Local 1i data 0, that's that memory location. OTE, local 10 data 1. In the manual, I had you compare the string of text to the right of the designation rung 1 and the display configuration in the ASCII text with that rung of logic. Because there are some people that sit and type in the logic in this form and don't actually use these symbols. Now they end up with these symbols because if you create a new rung with those symbols, when you hit enter, the rung's going to pop in here in this form, not in this form. But I have met folks people, engineers, technicians, that program more with text than they do with icons or symbols. Notice this says in neutral text. okay? You can also select an ASCII text. Now watch the line there. See, you saw some delimiters disappear. See, you've got open parentheses, close parentheses, open parentheses, close parentheses. In an ASCII text, you've lost the parentheses and you lost this semicolon on the end when you went to ASCII text. This is actually what I see people type in. They type in ASCII text, not neutral text. Personally, I prefer the ASCII text. More readable than the neutral text. We are at a beginning level here, so we're not going to worry about this, whether it's ASCII text or neutral text. I just wanted to point that out. You do not need to remember these details to write programmable automation controller programs for the Logix engine. This is shown to emphasize that this logic is just text, and you can edit text any way you like. If it looks right and your rungs are accepted, no E's at the head of the rung, then it is right. The context is good. And remember that if you export your logic, you can export it to a spreadsheet or to a Word document, and it's going to look like this. So you could actually write your logic in a text editor and then import it into this routine, and it's going to look just like this. Okay, save your project as beginner L, whatever your processor number is, OTL_OTU. We go up here and we look at what we have. We want to go to File, Save As. We go down here to 2 rungs with in out, L_OTU, and there you have it. Beginner L31 OTL for output latch, _OTU for output unlatch. Save. Now, it's probably better to save the program before you start editing it, just to make sure you don't accidentally overwrite the older program that you needed to start this one. Download and go online with your program in the remote run mode, all input switches in the off position. And by the way, make sure that you turn on your digital field device simulator. Communications, who active, wait till it sees the processor, it sees it, download. Remote run mode, we could do it with the key switch or from the online menu. I typically do not use the key switch because I'm probably sitting at a table on a chair out on the factory floor with a wireless router that I have in the control panel or connected to the controller. In the control panel, I could be sitting 100 yards away. I'm not about to run over, open the panel door, and operate the key switch. Typically, I always do it from the online toolbar. Might as well get used to it. Okay, all switches are in the off position, and in the manual we pointed out that this bit is off, and that makes this instruction true and turns this bit on. This bit is off, so this instruction is true. That turns this bit on. This bit is off, same bit in memory. Therefore, this is false. It turns that bit off. If I flip the switch, this is false and this is true. Because this is false, it turns off that bit in memory. Because this is true, it turns on that bit in memory. These are 2 different bits now. We're not still exercising OTE instructions against the same bit in memory like we were before. You normally don't write code that way. We did that to demonstrate a behavior in something not to do. This is more typical of what would be correct. If the switch is off, then that indicator is lit. If the switch is on, then this indicator is lit. And you can see that on your digital field device simulator. The 2 illustrations in the manual, if they're not totally clear to you, stop and work with it until it is, or back up and start over. Do not proceed unless you understand the difference between read-write, true-false, and on-off. Now, it just so happens that on our digital field device simulator, that this bit, or we'll say the circuitry connected to the screw terminal that influences that bit in memory, has a special input if you have the digital field device simulator. in the on position, which it is right now, if I push the push button next to it, it goes off. There is a normally closed contact, and using a symbol that looks like a normally closed to turn something on. Now you could go double negative in your thinking if you want. I wouldn't, because the fact that this screw terminal is connected to a normally closed push button at this moment has nothing to do with this symbol that looks like a normally closed contact. It separates those that do from those that don't. That is not a normally closed contact. That's not a normally open contact, although these symbols did originate from those electrical symbols. And this symbol right here electrically would be a normally closed contact controlled by a coil, a relay coil. This would be a normally open symbol controlled by a relay coil. If the coil is de-energized, then this is closed. If the coil is energized, then this is closed. You could say that if that coil or that bit in memory is off, then that contact is closed. If this bit in memory or coil is on, then this contact is closed. You need to forever walk away from normally closed, normally open when looking at relay logic. True if off. This instruction is true if that bit is off. This instruction is true if that bit is on. Next thing we want to do is, we could double click, by the way, on rung 0. We could double click and puts it in the edit mode. We'll close that. However, I wanted to show you another method, and that is if you, and look up here, see that that's grayed out, start pinning rung edits until I pick a rung. Now it's not. If I click on it, that puts it in the edit mode, the same as if you double clicked on the head of the rung. I find it easier to double click on the head of the rung than to actually use this button up here. You see that's two ways you could do it. You could double click on the head of the rung. You can select the rung and then select this button, start pinning rung edits, or you can right click on it, start pinning rung edits. You see the same symbols you see up there for the button. That puts it in the edit mode. Okay, we're going to open up this instruction. You were not able to do this with the MicroLogix, but if I double click on the instruction, I can bring up a list of instructions. You see there's quite a few. Considering that most of these you can expand to expose quite a few more instructions. I don't know how many there are here, but there's a bunch. However, we're after the easy stuff. We basically want to change this to an OTL, output latch. Double click, it's an OTL. I could very easily have done the same thing by double clicking and then editing the E to an L and then hit enter. So we'll do that with this one. Double click, well, it's not in the edit mode. Put it in the edit mode by double clicking. Open it up, and then I can replace it with a U. It doesn't have to be uppercase, but it goes in as uppercase. And there we have both rungs edited, which you did in your manual. In the manual, I did this as slightly different order. Nonetheless, it will work out the same. It appears that you have 4 rungs now, 0, 1, 2, and 3, and indeed you do. However, rungs 1 and 3 with an R in front of them, see the lowercase r? They are the 2 rungs that are actually running right now. So if I flip the switch off, see they do change state. And it looks like all the rungs are running, but they're not. Only the ones with the R in front, with the power rail highlighted, these are not running. They are in a insertable form, I for insert. While watching the state of the logic and with the switch represented by memory location input data 0, and with the memory location output data 0 controlled by the logic, alternate the switch from on to off positions repeatedly. Now we already did that, and you can see that it does show whether these instructions are true or false, and it shows whether these bits are on or off. Does the animation highlighting of true, false, and on off in rung 0 depict the state of the instructions and bits in memory? Yes, it does, because the highlighting reflects the true false condition here The highlighting over here reflects the on-off condition. The reflection of on-off here, the fact that that's a latch and that's an unlatch instruction, is irrelevant to the state of those bits in memory or the state of these instructions. So it's the state of these instructions and the state of these bits in memory. How many rungs appear to have influence over the memory location local 1 output data 0? Well, you might say that there's 2 that appear to have influence. How many actually do have influence? Only 1. This one right here, the one that's actually running with the lowercase r's. The I's in front of rung 0 indicate that this rung is untested and ready to be inserted in place of rung 1. The R's in front of rung 1 indicate that it is R for running. Put rung 2 into the edit mode as you see in the manual and open your instruction. It was an OTE. We've already done this, but I'm going along with the manual. With your cursor placed just to the right of the OTE, press the backspace key, then U, and then enter key. Edit the address bit to be 0. So now we're changing the memory location. We can't edit this rung. We have to edit this one, the one with I's in front. We double click there. We can backspace 0, enter. Okay, now we've got our editing done. Now you have 4 rungs of logic. How many are just proposed edits? 2. Which ones? Rung 0 and rung 2. 1 and 3 are running, 0 and 2 are proposed edits. They're there for you to see what you've done as a proposition or a preliminary edit, but the edit is not actually finished. You're editing a copy of rungs 1 and 3. How many are actually running in the program execution? 2. Which ones? 1 and 3, the one with R's in front of them. Try to edit the instructions or memory locations within the rungs of logic that are actually running. Were you able to? In other words, can you edit this tag right here? Double click on it? Nope. Double click? No. So you can't edit a rung that is running. So the answer is, were you able to, is no. We have 2 rungs of logic in the edit mode. You can finalize all edits with just a few clicks by clicking on the Finalize All Edits button. That's this one right here. Finalize all edits in the program. We used to call that the lawyer button because with RSLogix 500 and RSLogix 5, the lawyers wouldn't let Rockwell Automation, Allen Bradley, have that Finalize All Edits. You had to accept, test, and assemble, and it took 3-4 mouse clicks in order to what you can do now with just 1 or 2. So we'll click on that, and this would finalize all edits, so we'll say no. You can right click here and you can accept pending rung edits. That's what we're going to do. So we're only working with rung 0 now. We'll say rung 0 and 1. Accept pending rung edits. Notice now that's capitalized, uppercase R and uppercase I. That means that it's been accepted, but it's still I for insert. Then you could go up here and do a test accepted, program edits. You've accepted the edits, now you can test them. Now they're tested, and you can assemble the accepted program edits. And now rung 0 has replaced rung 1, but now it's just rung 0. Double click on rung 0 to put it back into the edit mode. Then select Finalize All Edits. Yes, and you're done. Unless, of course, there's errors or problems. Now, in this case, there's no errors and no warnings. And there's not even minor warnings about duplicate destructive bits that we had when we had 2 OTEs addressing the same bit in memory. See, now we have 2 instructions addressing the same bit in memory. First thing you notice here, since we have that switch on, the switch in the field circuit that's connected to the screw terminal on the input module associated with this bit in memory is on, but this is not on, because this instruction says if the rung is true, turn off this memory location. This instruction says if the rung is true, then turn on this memory location. Here is the logic as we have it now. If the switch is off, then latch that bit on, turn it on. If the switch is on, then turn it off. We're addressing the same bit in memory with these two instructions. Whereas in the other application, we were addressing the same bit in memory, but those were OTE instructions that have a true and a false execution. These do not have a true and a false execution. They only have a true execution. The difference in these two sets of rungs is that the earlier version with OTEs, output energized, had output type instructions that had a true and a false execution, and if the IO update came at the wrong time, it changed the output in between the two rungs. The current logic is using output instructions, or you could say rung 0 is using an instruction that has a true execution only, as well as rung 1. Both of those output type instructions, OTL and OTU, have true execution only. If the rung is false, they don't do anything. These two instructions together simulate an electromagnetic switching device called a latching relay. You all know that a relay is a switch operated by an electromagnetic field influencing the position of that switch. When you energize the coil, the position changes. When you de-energize it, it returns to the normal or resting position. A latching relay has contacts that are mechanically latched in the energized position and remain so even if the relay coil de-energizes, hence the term latched. To unlatch the contacts, there is a second coil, an additional coil, that influences the locking mechanism to release the latched contacts when the second coil is energized. The coils are named set and reset respectively, latch and unlatch. So there are two coils. So when you look at our instructions here, these are two different coils, but they're addressing the same bit in memory. So see, this departs somewhat from a real tight analogy with a relay coil and contacts. Nonetheless, this turns the bit on if the rung is true, this turns it off if the rung is true. As with the latching relay, once the latch instruction is executed and the bit is set to 1, repeated changes of the state of the rung have no effect at all. This is because the OTL does not have a false execution like the OTE does. Consequently, the OTU instruction can reset a bit to 0, but repeated execution has no effect whatsoever. So if this were an actual latching relay with two coils, electromagnetic relay, and we turned on that coil to latch the contact open, then if you continue to exercise this rung, false, true, nothing's going to change here, and it wouldn't on an actual relay either. Because if you turn on the latching coil, the contact changes position and latches. If you turn it back off, it doesn't unlatch. If you turn it back on, it doesn't latch again. Once it's set, it's set. Consequently, with the unlatch instruction or the unlatching coil on a real electromagnetic relay, if you turned on this coil and unlatched the contacts and let them go back to the resting position and then turned off the voltage here and then turn it back on again, repeatedly energizing this coil cannot further unlatch the contacts. These instructions do work identical philosophically to a latching relay. Next, we had you take and grab a rung up here, mouse over, bring it down. See, you got these are rung mimes. There's many mimes, but you see that the instruction mimes don't light up when you are dragging a rung. Then I had you add some instructions. I had you add a true if off and an energize output. Then I had you mouse over this tag, not the instruction, the tag, hold the mouse down. Now you're looking at memory location mimes or tag mimes, not the same as a rung mime, not the same as instruction mime. Drop it here and then mouse over this one and drop it here. Then we had you edit the tag name, finalize all edits. Now you have a third rung, but it's not working with the same memory locations of the first two rungs. Looking at our logic as a whole, including our new rung, rung 2, which output bit does the state of local 1 I data 0 influence? This bit right here, same bit, local 1:0.data.0. Which output bit does the state of local 1 I data.1 influence? Just this bit. So we have two instructions here influencing this bit, and we have one instruction influencing this bit. To emphasize the difference between an OTE that has a true to false execution and an OTL with a true only execution and an OTU with a true only execution, we have this logic in front of you. The manual says, while observing the state of the two output bits, which are these two bits right here, 0 and 1, flip both inputs to the on position, take a look at the state of those bits, 0 and 1, and then to the off. Do you see any difference between the influence of input 0 on output 0 and the influence of input 1 on output 1? No. Occasionally we like to substitute input 0 for bit 0 of the input module's data word and the same for bit 0, output 0 of the module word's data word. In other words, the language in the manual, we like to substitute some of these other tags that we showed you how to create just in case you did not have an IQ6 XOW4. So once in a while we'll remind you that you are maybe using some different I/O structure. I hope not, because for the cost of an IQ6 XOW4, which you can buy them for as inexpensive as $70, $75 on eBay, I purchased quite a few of them, never had one that was bad. I had one that had a broken screw that held the removable terminal block to the module, but it in no way affected its operation. I'd hate to think that for the want of $75 that you have introduced this convolution into your learning process. Nonetheless, once you get used to it, you're used to it. It's not going to hurt a thing. Using the editing procedures that you have learned, edit the instruction types to that shown in the next illustration. And basically what we're going to do is we're going to flip around the states that control the on and the off of the output bits. I'm going to do that really fast. Double click, double click, double click. Change that to an XIO. Change this to an XIC. Change this to an XIC. Finalize all edits, and we'll see if I got myself in trouble here by doing this on the fly in a hurry. So this is exactly what we show you in the manual. Before, this was off and this was off and all these showed on. Now, without changing the positions of the switch, we change the instructions to be true in the opposite state. And you see you have the exact opposite thing over here. This is just to prove a point. So if I turn these both on and both off, do you see any difference between the influence of input 0 on output 0 and the influence of input 1 on output 1? This is just to show you that in this form, that if you want to use an input device to turn on a bit when it's on or off in the opposite state, you can use a latch unlatch, or you can use an OTE. You will see much better use for the latch and unlatch, because obviously this rung of logic right here, where you have it's true if on, or it could be true if off, but you have a true and a false execution, is less programming than doing two rungs. So this is not a good use for latch and unlatch. What's the difference between the logic before the last edit and the logic now? Well, we basically said it. What we did is we changed or reversed the true state for that bit in memory and that bit in memory. So now the logic is just the opposite. If input 0 is on, then we latch output 0. If input 0 is off, then we unlatch it. And vice versa down here, vice versa. If input 1 is on, then we turn on output 1. If input 1 is off, then we turn off input 1. Okay, save your project, and we're done with this section. By the way, when you save your project, you don't always have to upload tag values before saving the project. Personally, I think it's a good idea. There's only two conditions or scenarios where I would not upload the tag values. One is if I did some things online, I made some edits, but I don't want to take the online data table values, tag values, and upload them over the top of the ones that I already saved, because the ones that are saved offline on the hard drive or in RAM are the ones that I want to keep. Or you just want to save time. If I say no, in this case, I don't care what those tag values are. I just don't want to waste the time waiting for it to upload the tag values, then save the logic.